And I realized I didn't record the first like 15 minutes of class. Apologize for that. What we did in the first 15 minutes is went over the syllabus, which is on the Google Classroom. Talked about the homework that's due. It's also posted on Google Classroom. So yeah, this trig homework, sort of draw a picture of the setup, and then using the triangle you drew, can you find expressions for the tangent of the cosine inverse of x? So for the tangent of that angle theta, for the tangent of that sine inverse of x. So this is something you may or may not be familiar with, but we will use it like later on in the course to do the calculus. And I actually posted 3 videos. So I've got a series of calculus videos, and I posted 3 videos that are relevant to this. It's like how to find like the cosine of arc cosine. And here's like how to find the cosine of like inverse sine. And you can watch these if you want like a refresher on how to do this. And you'll see me explain like what does it mean to draw a picture of the equation and how do you use that picture to do a similar problem. So you can see me like go through that and do it. And the videos are only like 5 or 6 minutes long per viewing. I won't watch any of it with you right now because like I'm not sure how to make the audio go through on Zoom. I'll just go through, like there's a setting I have to modify. I don't like reacting to my own calculus videos, but they, you know, they are useful. So we'll probably do a little bit of watching together, like as we go through. But just so you know, that's there. It's due February 15th, 5 p.m. That's this Monday at 5 p.m. So get a head start on that so you can then ask me questions in office hour and during class. So any questions about any of that? So I want to start out today then going into chapter 2. So we've done a little bit of pre-calculus review, and I've given you some homework to help you review a little bit further. Like one of those problems for homework is completing the square. So you may even need to like go back and look that up, but I trust you to do that and to ask me if you've got any questions. And for today, I want to start introducing the fundamental concepts that become the calculus class. So let's get into it. So mic check, now that I'm away from the computer, you can still hear me just fine?
Yeah.
Yeah, okay, great, thank you. Feel free to jump in any time and ask questions in the chat or verbally. So from algebra, you know that if you do something like in algebra, we look at these linear functions, these lines, right? So you write something like 2x plus 1 in a typical algebra problem is to say, okay, well, like, can you graph this line? And you might say, okay, well, the y-intercept is equal to 1, and its slope is equal to 2. What's slope of a line? It means that if you go over, if x travels out by 1 unit, then the y value is going to travel up by 2 units. So you get this triangle. So you go over by 1 and up by 2, and the slope is like the rise over the run, the change in y over change in x. So slope is like, see this notation, delta y over delta x. It's like if you pick 2 points, you pick 2 points, like these 2 points, like x1, y1, which in this case would be something like x equals 0, y equals 1, and you pick your second point. I mean, you can pick any 2 points that are not the same, but it happens to be 0, 1, and then 1, 3, but be any 2 points on the line. In this case, this second one happens to be x equals 1, y equals 3. So you pick those 2 points, and delta y is notation for y2 minus y1. Pictorially here, it's equal to 2. It's this vertical length delta x. That's notation for x2 minus x1. In this case, it's just equal to 1. So depending on which 2 points you pick, you'll get a different delta y, different delta x. But for a straight line, that slope is constant. Doesn't matter which 2 points you pick. It's always going to be equal to 2. So calculus answers a different problem, like a more general problem. It says, can you generalize this idea of slope of a line, but to a different function? So it says, look, so suppose you have some other function, like a logarithm or sine function, or y equals x squared, or like whatever you like, but just schematically, I'll draw a function, and I'll pick some point on the function. So here's like some x1, and here's some point x1, y1. And so is there like a sense where you've got like slope of a function, and it doesn't really necessarily make a whole lot of sense, but we can try to make sense of the idea. So we can still certainly pick 2 points on a general function. Like, let's say, here's my x2, my y2, and here's my x1, my y1. And for these 2 points, like, I can certainly still draw the straight line between them. Like, nothing stops me. I don't know if this different color will show up. I'll try to put it in orange. And you can still look at delta y over delta x. In other words, you can still look at this slope of the line that goes through x1, y1, and x2, y2. And so the orange line is what we call a secant line. So a line is a secant line if it's a secant line for some function if it goes through, if it's the straight line going through 2 points on the graph of that function. I'm just trying to check and see if that's sort of visible. And then this quantity delta y over delta x is called the average rate of change. So average rate of change, and you'll hear it stated like average rate of change on an interval, like average rate of change on the interval from x1 to x2. The idea being in your mind that like here's an interval from x1 to x2 in the x-axis. You're looking at this portion of the graph over x1, x2. And you're saying on average, how much is that y value changing? And the way you figure that out is you say, okay, well, let's just look at the y value here, subtract the y value there. That's delta y, and then divide by x2 minus x1. So the change in y divided by the length of the interval. So any question or comment on that? And a little later in the class, I'll have you do an example. Actually, I'll have you do an example right now. So I just drew something in general, but you can pick something. So you can use a calculator or use Google or Desmos or whatever you want to help you with the calculations if you like. But let's pick f of x equals x squared. And let's find the average rate of change of f of x on the interval from 1 to 3. So take a minute and please calculate that out. You should get an actual number for that. And private message me any question or yell out a question, and I'll mute myself and give you a minute to work. Okay, after giving you a moment, I'll show it and then I'll give you another chance to practice. You don't have to draw a picture to do this, but why not? It's a schematic picture of f of x equals x squared. You can see I haven't labeled my x and y axis. So it's just schematic. And so we're trying to go from, yeah, in reality, this thing should be like going upwards faster, but it's kind of easier to see if I don't draw it quite so accurately. So 1, 2, 3, 4, and I'm looking at x equals 1 to y equals 3, and when y equals 3, you're supposed to go up to, when x equals 3, excuse me, you're supposed to go up to 9. So like 1, 2, 3, 4, 5, 6, 7, 8, 9. So maybe you got, obviously not exact, of course. It's 1, 2, 3, 4, 5, 6, 7, 8, 9. And you just want to calculate delta y over delta x, which is y2 minus y1 over x2 minus x1. That is to say, it's the slope of the secant line from x equals 1, the point over x equals 1, to the point over x equals 3. So this point is like 1, 1, and this point is like 3, 9. And then you can think about drawing the line between them. And then the slope of this secant line is the average rate of change of x squared on the interval from 1 to 3. So you have to know what's x1, x2, and what's y1, y2. So here's x1, x2, y1, y2. Those are the coordinates of the 2 points that you use to determine the secant line. Where do you get those 2 points? The x values are the boundary of this interval. So it said find the average rate of change on the interval from 1 to 3, telling you your first x coordinate is 1. I plug in 1 into x squared to give me 1. That's my y coordinate. My second coordinate, x coordinate, my x2, is 3, and therefore my y2 is 3 squared equals 9. And so y2 minus y1, so that's 9 minus 1 over 3 minus 2. So it's the ratio of this length to that length. So it's 8 over, 3 minus 1, excuse me. 3 minus 1. So it's 8 over 2 equals 4. So the average rate of change of f of x equals x squared on the interval from 1 to 3 is equal to 4. So it's sort of like just an algebra concept, slope of the line, but now applied to like a particular situation. But we want to go a little bit further. So we want to say not just like how much is a function changing on average. We want to say like how much is a function changing like instantaneously, like right at this point. And a way that you can kind of get to that is you can say, okay, you can say to yourself, okay, I'm interested in like what you might call an instantaneous rate of change at the point 1, 1. How do you conceive of something like an instantaneous rate of change? So think of it this way. Think of this graph. Think of the y value as being like your distance from home. So you're at home, you get in your car, and you start driving away from your home, and y equals x squared is your distance from home, and x is like the number of seconds that have elapsed. And so what we're saying is, okay, if you look at yourself 1 second after you left, and then look at yourself 3 seconds after you left, then maybe like if your distance was in feet, then you could say your average rate of change, which is like your average speed or average velocity in this case, you could say that's like 4 feet per second. It's like a physical way to interpret the example, for instance. If you think of this graph as telling you your distance, and is that difference has this parabolic curve that tells you that you're speeding up. But you don't want to know just on average how fast you were going in between second 1 and second 3. You want to know like your actual speed after 1 second. You want to know instantaneously how fast you're going. So you want to know your instantaneous velocity. When we think of it as distances and seconds, then we call it instantaneous velocity. If you just think of it as a general function, then you would call it instantaneous rate of change of the function. So how can you do that? Well, what you might try is you might try picking a point that's really close to 1 second, you know, like it's like 1.2 seconds or something. The color might not show up that well, but I'll put it in yellow. And that's still like an average rate of change, but it's on a much smaller interval. And so you might get the idea that you can just kind of get closer and closer, right? Take the average rate of change not just on 1 to 1.3, but also on 1 to 1.2, 1 to 1.1. So you could imagine like fixing this 0.11 and then thinking of your other point kind of like sliding in and observing how those individual average rates of change get closer and closer to, as you get closer and closer to 1,1. And so you could ask yourself, do those average rates of change appear to be converging to like a single number? So I'll draw pictures of the secant lines. They all start here and go to the various points. And eventually, the secant lines, they all start to kind of settle. They all start to kind of settle. And I don't have another color to give it, so I'll just use the white chalk. They all kind of approach this one line, which is tangent to the curve at that point. So we call it a tangent line. So if you can draw all these secant lines with the one point getting closer and closer and closer to your fixed point, if those secant lines settle down and converge or limit to like a single line, then that line is called a tangent line. But let's not get ahead of ourselves. Let's actually try to do this. Let's actually see if we can calculate or get an idea for our instantaneous rate of change or instantaneous velocity. So what I want is like an estimate my instantaneous rate of change at x equals 1. And so what I want to do is I want to calculate some average rates of change, make a little table. So interval, I'll put an interval here, and I'll put average rate of change there. And so you've already calculated from 1 to 3, you've calculated average rate of change was equal to 4. So now I'll ask you, please calculate average rate of change from 1 to 2, average rate of change from 1 to 1.5, and definitely use a scientific calculator for this. Or if you don't have like access to your phone or calculator right now, you can type in the calculations into Google and it'll come back and show you. Oops. And after 1.5, let's do 1.2. And then let's do 1.1. And I'll ask you if the average rates of change, if those slopes of all these yellow secant lines appear to be settling down to a specific number. So is that clear how I'm asking you to calculate average rate of change for interval from 1 to 2, 1 to 1.5, 1 to 1.2, and 1 to 1.1? And if you've got your own paper, then you can make your own table and please fill it in. And let me give you a few minutes to do that. Okay, so now that I've given you some chance to work, and you're welcome to keep working, I want to exploit the fact that we're online to share with you my solution to this on Desmos. Sort of show you what I've got going on. So here's the function f of x equals x squared. And this a equals 1 is just telling me to start with x equals 1. And h is my step size, like how far to go. So with a equals 1 and h equals 2, that's telling me to go from x equals 1 to x equals 3. And this m calculates the slope of the secant line. It's the difference in the y values, a plus h minus f of a over h. And we calculated that to be 4. And I can even show you a graph of the secant line. It's y equals, well, there's the formula there. And this is going to let me change the slider to get the different variables. So if I go from 1 to 2 instead of 1 to 3, then my step size is just 1. So I'll move h down to 1. And you can see the secant line changing, right, as I change the other point, and it slides on down to 1. And the slope was a little less. This time the slope was equal to 3. So the average rate of change on the interval from 1 to 2 is now equal to 3. And then my next one was 1 to 1.5, so that means the step size changes to 1/2. You can see it sliding on down. Change that step size to 1/2, I get 2.5 as my slope. Next one was 1.2, so its step size changes to 0.2. My slope is now 2.2. Next one was average rate of change from 1 to 1.1. I'll zoom in a little bit so it's easier to see. Zoom on in there. So you can see those secant lines are getting pretty close to the function, at least when you zoom in. For 1.1, changing my step size to 0.1. I get slope equals 2.1. And so it seems like those slopes are limiting to the point 2. And maybe I can even change the values on this slider, so h can only go from 0 to 1, give me more specificity there. And as I slide h down, getting closer and closer to 0, you can see that slope getting closer and closer to 2. And you can see the secant line getting sort of closer and closer to what's going to become the tangent line. So as that second point converges onto the first one, well, yeah, you need 2 points to make a line, but as the second point converges onto the first one, this secant line, this collection of secant lines is going to limit to one single line with slope equal to 2. And that's going to be the tangent line. And so the instantaneous rate of change at the point x equals 1 is going to be equal to 2. So that's pretty neat. Are there any questions about that? By the way, there's a name for instantaneous rate of change. It's also called the derivative of the function at the point. So this is your first introduction to what's a derivative. We'll talk about that a lot more, but we need to explore later on this concept of like what's a limit. You know, we've been talking about like the the secant lines, making a limit to a tangent line. We've talked about those slopes, making a limit to the number 2. So we need to explore that concept in just a little bit more detail. But once we do that, then we'll be really ready to talk about limits. And so I think it's pretty close to 12:05, so we can stop for today. So thank you everybody for your time and attention. Don't forget to attend to that homework due on Monday. Ask me any questions. Come to my next office hour, 2:30 to 4 on Thursday. And it's great to see you. I'll see you on Friday.
See you Friday.
Take care.
Thank you.
Thank you. Have a good day.